Questions about anything? The homework is due tomorrow night at 11:30. Well, I want to say some more about basic calculus of analytic functions today. Before I get rolling, I mentioned at the end last time that that procedure I showed you to come up with a harmonic conjugate, well, it works beautifully in a case of a rectangle domain or a disk. And there's a situation when it might not work, and that is if a domain has holes. And I thought I ought to give you the classic example of a function where that exact problem comes up. Namely, u equals the natural log of x squared plus, that square root of x squared plus y squared. That's the natural log of the modulus of z. That turns out to be the real part of a complex log function. We'll see that soon in the next couple of lectures. But if I were to try to, you do that routine that I did last time on a disk or a rectangle, you do that routine of solving the Cauchy-Riemann equations, and you find out that you get a harmonic conjugate, which is the principal argument of x plus iy. Plus, and remember, you always get an arbitrary constant when you do the calculations. So that would be a harmonic conjugate on a disk or a rectangle, by the way, that not containing 0. So a 0 is not an element. The origin is not in that disk or rectangle. In that case, you get the principal argument. And of course, the principal argument is the principal arctangent of y over x. So that's a real value, that's a real function. And so when you think about, if I tried to come up with a harmonic conjugate on a domain with a hole, and the hole included the origin. So for example, let's do an annulus. Okay, when I try to, I've got this u function, that's harmonic. And it's harmonic on this shaded region, which is an annulus, has a hole. And if I were to try to cook up a harmonic conjugate over here, say, I'd get the principal argument plus a constant. I could do it over here on a rectangle. I'd get the principal argument plus a constant. And the thing about the principal argument is that it has a jump. And the jump is over here. Remember this branch, did I call that a branch cut? Minus pi and plus pi. You can't decide who wins there. And so you have to, and so the thing has a jump right there. So if I try to start out with a v over in one of those, that little disc, the purple disc, and try to sort of piece them together, when I get to that spot, I run into an issue. And that's exactly the hang-up with a hole. So the ouch is right here. I can't hook them up. Can't hook up the v's that I get by that calculation, which are unique up to addition of a constant. So it really is an impossible problem. Questions about that? Yeah.
Could you reiterate how the hole causes the hooking of the v's? I think I got a little lost.
Well, the argument, remember we had to say the principal argument was the angle and between minus pi and pi. And along the negative real axis, that's where it fights for who gets that. Is it minus pi or is it plus pi? And so if you look at the graph of the arg, it's minus pi when you're coming at it from the bottom, and it's plus pi when you're coming at it from the top. And so they don't hook up there. They have a jump, discontinuity. And so that certainly is not harmonic if it's not even differentiable. In fact, not even defined at the jump. So that's a hang-up. Let's see, maybe I should say, when I do this, that I should take minus infinity 0, not in the disk or the rectangle. Anyway, well, I'll say more about that as we get more comfortable talking about the complex log functions. So let's see, I want to do more basic facts about analytic functions today. Which are complex differentiable functions on a domain. On an open set. Let's see, one basic fact that I've already demonstrated is that analytic functions must be continuous. We did that last week. Basically, it's the same proof you do in freshman calculus. And then because of that proof, when you look at that kind of thing, you realize, oh my gosh, all those basic proofs go through. And so the rules of differentiation R to R hold C to C. And so let me show you, let's see, I showed you that. And I also showed you that Z bar is not complex differentiable. Because the Cauchy-Riemann equations fail. And so you have a couple homework problems where you got to think about fancier things than Z bar. So how about do an example here? Example, the modulus Z squared plus Z cubed. Let's call that f of z. Question is f C differentiable? Okay. Well, let's think about that. Well, if it were, let's see, I want to write f of z like this. F of z, the modulus of z squared is z times z bar plus z cubed. So if I start thinking out loud, if f of z were complex differentiable, if f were complex differentiable, then so is f minus z cubed. And that's equal to z times z bar. And now I've got z times z bar. I know that z bar is not complex differentiable, and I know that the rules of calculus work for complex numbers. And so now my brilliant idea is, if f is C differentiable, then ... so is f of z minus z cubed divided by z. And that's equal to z bar. Let's see, so I maybe should say, I'm using the rules of calculus from freshman calculus. I divided by something there, it better not be 0. So is 2. And you got to say, add when z is not equal to 0 at least. But z bar is not differentiable, it's not complex. Z bar is not. So f can't be. If it were, we get a contradiction. That's how I would go about doing the problems in the homework there. The book uses in that section, I like that book a lot, but I certainly don't like that little section there. It goes through a song and dance, which I don't really approve of, about complex functions that are admissible. And it just didn't, I never heard anybody talk like that before. I don't talk like that. So song, a dance about complex functions that are admissible. It's fun to read that. Which is not standard. And I guess being admissible means that it's a function of z and no z bars. So the feeling is, giving the feeling of a function of z, but not z bar, with no z bars. So that's not standard terminology in any book that I'm aware of. But I guess it's a good thing to think about that. That's the basic feeling of being analytic. Since functions are going to be expressible as power series, if they were written in terms of z's and z bars, the z bars better go away. And it's because of this argument above that you see that, oh my gosh, z bars are bad. So it's not standard. Just something to be aware of. I guess I'm up to number 4. Last time I gave you a quick proof that if f prime is identically 0 on a domain omega, then it's got to be constant. So let's see. If f is analytic on a domain omega, and the derivative is identically 0, then f is constant on omega. Complex constant. And today I want to give you a more sophisticated proof than I did last time. Last time I referred you to Math 261, multivariable calculus, to wimp out and give you a simple proof. So here's the second proof. I would call this a better proof. The book does this proof. Here's a better proof than last week. In the spirit of my favorite subject called complex analysis. So here it is. Let's write like we do. F of x plus iy is u of xy plus iv of xy. Then we know that the Cauchy-Riemann equations hold. If the thing's analytic, we know the u's and the v's have first partial derivatives and satisfy the Cauchy-Riemann equations. And of course, u and v are continuous also. So I guess I should say, here's what we know. We know u and v are continuous. That was number one. And first partials exist. That was an important consequence of our discussion of the Cauchy-Riemann equations, and satisfy the Cauchy-Riemann equations. Let's see, the Cauchy-Riemann equations we figured out by writing f prime of z equals, red box number 1 was du dx plus I dv dx. And red box number 2 was dv dy minus I du dy. Well, if the derivative is 0, it means all those first partials are 0. That would imply the gradient of u is identically 0 vector, and the gradient of v is identically 0 vector. From those, from that red box number 1 and red box number 2. And last time I showed you, well, that implies that, let's see, so here's the thing. Last time I assumed that the partial derivatives were continuous, and I was able to deduce that. Today I don't want to assume that. So last time I assumed first partials were continuous. Turns out you don't have to do that when you think about it sort of in a complex analysis spirit. You don't have to do that, and I won't do it today. Okay, so a freshman calculus fact that I'm going to use right now. It's about real functions. If h of t is continuous on a closed interval, on closed interval AB, and f prime of exists, f prime, not f, h prime of t exists on AB, on the inside at least, and is equal to 0, then h is constant. When I teach that in freshman calculus, they're not terribly impressed, because that means when your speed is 0, you're not going anywhere. Everybody believes that. But from a philosophical point, if you believe that, you better be able to explain why you believe that. And that was the beginning of advanced thinking in math. Then h is constant. In fact, because of continuity up to the endpoints, it's constant on the closed interval. And the proof was the mean value theorem, which the freshman calculus class was also not very impressed about, but it's a very important tool. So the proof is mean value theorem, period, basically. Okay, so now I'm going to prove my fact on a disk first. The proof of number 4 on a disk, just to get rolling. So, I've got a disk. Here's the center of the disk. And here's a point Z in the disk. Because I have this freshman calculus fact, I would like to deal with functions of one variable. And the way to do that in this picture is to first go horizontal here. And then go vertical to Z. And now if you think about the functions on the green part there, remember the partial derivatives are you hold one constant and you'd hold y constant on that green thing, and you'd let the x be a variable. That's how you calculate partial derivatives. And so on that green line, we know that du dx is identically 0. And so that's a one variable thing. The y is being held constant. In that calculation. And so I've got a one variable function of x, and its derivative is 0. And so the freshman calculus thing implies that u is a constant. Let's see, and the same is true about the dv dx. So u and v are constant along the green part. Okay, so it's constant over to this spot right here. And now I do the vertical one, and that's where I would use the fact that on the pink part, du dy is identically 0, and x is being held constant. And so it's really a function of just y there. And that partial derivative is 0, and the dv dy is also 0. So uv is constant along the purple. On the vertical. And of course, it's the same. You start at A, you get the same constant at the end of the green one, and then you continue up to Z and get the same constant up to Z. So that's how you see that the freshman calculus, the calculus lemma, implies that U and V are at Z is what the same as A. So check. It's constant on the disk. All right. And now now that I've done it on a disk, it turns out I can think about it on a domain. And this is kind of a typical complex analysis argument. So here's the proof on a domain. Proof of number 4 on a domain. It's basically a picture proof. Okay, so I've got a domain. Turns out holes don't matter in this argument. So here's a domain. Make a couple holes. It's an open set, and being a domain means that if you give me any old 2 points in here, here's an A, and here's a Z over here. I'm thinking of A as a fixed point. Then we know that these since it's a domain, A and Z can be connected by a continuous curve. And we know if they can be connected by a continuous curve, they can also be connected by a polygonal curve, just by approximating by chords. And here's the argument now. I can look at each spot along these polygonal curves, and instead of going on the curves, I can do a zigzag. So I could go zigzag, zigzag. I know it's constant on horizontals and constant on verticals. Etc. I'm getting carried away here. There, made it. And so that argument about disks, I do locally to do a zigzag staircase thing. So I get a zigzag staircase curve. Joining A to Z. So joining a fixed A to a moving Z. I think of it as moving. I let it slide around. And use number 1. Use. Questions about that? That's a nice way of thinking. Well, I've been convincing you that a lot of these things are just freshman calculus. One of those things is a very important thing that you might not have seen a valid proof in your freshman calculus class. And I don't think I proved it in 341. I don't think it's in the book. I mean, maybe it is, but the proof of the chain rule. Did we do that in 341? I feel like I might have. Anyway, it's worth looking at the proof of the complex chain rule. It's about composing functions. If I write h of z as f of g of z, and I write w equals g naught, w naught equals g of z naught, and the fact is, if g is c differentiable, at z naught, and f is c differentiable at w naught, then h is c differentiable at z naught. And a famous formula, and h prime of z naught is f prime at g of z naught times g prime of z naught. Well, I told you that when you look at your freshman calculus proofs, they would just go over to the complex case. Well, some freshman calculus books, to make this believable and quick, give you a proof that isn't totally valid. And so I want to make sure I gave you a real proof that is valid. And you can do exactly the same thing in the real case. Questions? Let's see, so here's the proof. We know that f is complex differentiable at W naught. So when I look at the difference quotient, I know that that's going to tend to f prime of W naught. So the error would be, I'll write it here, E of W. And we know that's complex differentiable, so the E of W, that's not the exponential today, goes to 0 as W tends to W naught. So I can solve this for f of W minus f of W naught. That would be equal to f prime of W naught times W minus W naught plus E of W times W minus W naught. I'll put that in a box, not a red box. It's not that important. Now I'm going to let W be G of Z. And of course we know that W naught is G of Z naught. In that box. So then I would have f of G of Z minus f of W naught equals f prime of W naught times G of Z minus W naught is G of Z naught. I guess I should, as long as I'm sticking with this, I should put a G of Z naught here. Oh, plus E of W, E of G of Z times, I need to move this over. Times G of Z minus G of Z of naught. Okay, all I did was replace things in that box. And I realized, aha, that's the numerator in the difference quotient I want to calculate. And so that's the numerator, and if I put Z minus Z naught in the denominator, I get the difference quotient I want to calculate. And now when I distribute that over here, I'll stick it on this one, because that's where it belongs. And I'll stick it on this one, because that's where it belongs. And so that difference quotient that I want to understand, let's see, now I'm going to use the rules of calculus. That tends to, this is just a constant. So it just sits there. This one tends to, G is differentiable, so this one tends to G prime of Z naught. This one tends to G prime of Z naught. And the only one I have to think about is this one. I claim it tends to 0. And the Y, the purple one there, is important. Y, E of G of Z, tends to 0. It's because G complex differentiable implies G is continuous. So C differentiable at Z naught implies G is continuous at Z naught. And when you compose, it's a rule of limits now. Rule of limits. E of W goes to 0 as W goes to W naught. And so, and we know that G of Z goes to W naught equals G of naught, G of Z naught, as Z tends to Z naught. So, E of G of Z goes to 0 as W tends to W naught. Does this bother anybody? The G of Z might actually be equal to W naught someplace. So when you think about my rule of limits, I would need to be careful. I should have defined E of W naught to equal to 0 to make it a continuous function. So I could use the rule of limits. Even in case we have some G of Z's that are equal to W naught when Z is unequal to Z naught. In many of the proofs in freshman calculus, the error is when you divide by the G of Z minus G of Z naught to make a difference quotient game, you might be dividing by 0, and that's dangerous business. Questions about that? Of course, there's lots of different ways to demonstrate the chain rule. One way is to use R2 to R2 chain rules plus the Cauchy-Riemann equations. But I like this way better. Let's see, since we've got 10 minutes left, I thought I'd show you a famous calculation. It's a classic problem to motivate the complex exponential. Cook up the complex exponential. I'll call it E of Z. And that's a function with a complex derivative. So number 1, I guess the number 1 is that E of 0 should be 1. And number 2, its complex derivative should be itself. It's a fun game to do. So let's see, let's write, we've got red box number 1. E prime of z is red box number 1. If I write u plus iv is du dx plus I dv dx. And dv dy minus I du dy. And we want that to be equal to itself, which is u plus iv. And so that's going to give me 4 equations when I equate those two things. I'm going to get A. I want du dx to be equal to u. I want dv dx to be equal to v. Well, du by dx is kind of like an ODE, and there's just a y floating along. And that's a famous problem. The derivative is equal to itself exactly when it's like exponential growth or decay, depending on if the constant is plus or minus. So the solution to that problem is the classic, namely u is equal to a constant times e to the 1 times x. The k is 1 there. But y is floating along as a parameter. And so when I get a c here, I might get a different c depending on my y. So that c is might depend on y. You can see that that satisfies that differential equation. And in fact, using a very similar argument to my demonstration last time, that if first partials are 0, then the thing is a function of the other variable. You can use that here to see exactly that. I won't dwell on it. Okay, so that equation is going to give me that fact. This equation is going to give me v is a constant times also e to the x. But that constant might depend on the parameter y. So I've used up those boxes. And the other box gives me b dv dy needs to be equal to u, and minus du dy needs to be equal to v. Okay, I used up my boxes above. Now I'm going to use them in a different way. I'm going to take those boxes. Let's see, dv dy, I'm going to stick down here. And get that dv dy is k prime of y times e to the x. So where am I putting this? I'm moving it over here. I'm using it right there. And that's supposed to be equal to u. So I'm getting u closer now. And now I'm going to use this one over here. Minus du dy. I'm going to use this one right here and get du dy would be c prime of y times e to the x. And I want that to be equal to v. I'll call this box number 1 and this box number 2. Well, it turns out I can pin down those k's and c of y. Let's see. If I differentiate number 1, let's see, what do I get? Oh. want to call that number 1 yet. Remember u I had, u was equal to c of y times e to the x. And v was equal to k of y times e to the x, wasn't it? Right. And so when I divide out the e to the x's there, I get some ODEs for the k's and the c's. I get that k prime of y needs to be equal to c of y. And here I get that minus c prime of y needs to be equal to k of y. And it turns out that's a system of ODEs that's not hard to solve using Math 262 or 266. This is what I wanted to call number 1, and this is number 2. Number 1 prime, if I differentiate it, becomes a second order ODE kind of. I get k double prime of y equals c prime of y. And let's see, c prime of y from number 1 is equal to, from number 2, c prime of y is equal to minus k of y. This equality is from number 2. And so I get a second order ODE for the k's. K double prime plus k is 0. That's a famous second order constant coefficient, simple harmonic motion kind of Hooke's law thing. And so we get from this that k of y is a cosine y plus b sine y. And you can do the same thing with 2 prime. If I take the derivative of 2 and use 1 similarly, I get that C satisfies the same differential equation. And so C of y, it's going to be the similar thing. Maybe I'll call it a cosine y plus b sine y, little b. And finally, the last step is to use the initial conditions. Use e of 0 equals 1. Those initial conditions pin down all the a's and the b's. Initial conditions for the ODEs. It pins down A, B, and capital A, capital B. And we get the classic complex exponential. And so that's what I meant when I said that it's uniquely determined by those two things. We get e to the x plus iy is e to the x cosine y plus I e to the x sine y. Okay, that's a 10-minute thing that everybody should see. And I'll talk more about the complex exponential next time. Any last-minute questions about anything? Homework questions? Yeah.
How did k and y basically end up having the same equation of a plus y plus b sine y, even though...
Oh, it's the same differential equation.